Alright guys, so after I showed you how to solve for the resultant force and reaction forces, your first step was to explain to you that you have to draw the free body diagram. And I promise you that on your final exam or in any exam you'll take, your professor will most likely ask for the free body diagram, which you see here on your right. So now going back, remember this problem. Now what we want to do is we want to draw the shear diagram. First thing I want you to consider, when you draw the shear and the moment diagram, or either one, please do me a favor, get rid of this resultant force. Not here, because this is your free body diagram. You want to include this here, or else you might not get the full credit. However, when you think about the shear or moment diagram, please avoid thinking of the resultant force. It has nothing to do with what we're going to do here. Your most important forces are your reaction forces, which are on point A and point B. So what I want to do, I'm going to try to keep everything parallel to one another. This right here will be my plot for the shear, which I'm going to call V of X. Okay? This plot right here will be demonstrated as your actual shear diagram. So now what you need to consider when you look at this shear diagram is what is the first point on my y-axis counts. Well, you already solved for a reaction force, which is a 9 kilonewtons. So we know that the first point on this plot will be 9 kilonewtons. Okay, now the most other critical part now you got to go back into is solving using integral. The best way I like to do it that way, so that way you don't have to memorize a certain shape and then you kind of get an idea of what this diagram would look like. Best thing to do is knowing your formulas and then work your way from there. That way you don't have to actually memorize anything. The formula for the shear using integral form will be, let's say, V of X equals integral Wx dx. Okay? Our Wx at this point is known as our distributed load. But also keep in mind, it's not just a distributed load, it's more of the slope of this plot. So when I say a slope, what you really need to look at is this line right here. What is the slope of this line? Once you know the slope, everything else is just plug in. So what we want to look at is our slope in this case. We have x, every 9 meters, you go 6 kilonewtons. So what we need to do, we'll say it's the integral of 6 over 9 x. Remember this, guys. So if you actually plug this in, you will get this slope. We all know that anything half of x in your graphing calculator would look something like that, a linear line. Okay? After that, you put dx, and then you have to also include whatever that's in this plot. In this case, we already have a reaction force acting at point A. Since we're starting from left to right, 9 kilonewtons, it will be 9 kilonewtons. However, you also want to take a look back at this. This is not just 6 over 9 times x, it's actually negative 6 over 9 times x. The reason for that is because your actual distributed load is actually acting on the beam as pushing weight down on this beam. So basically meaning it's negative. If it was actually pushing on the opposite direction, it would be considered as positive. So please remember that. So now all you have to do is solve for the integral, which is really a basic integral. In this case, what we will have here, V of x equals negative 6 over 9 x squared times 2 plus 9 kilonewtons. You can simplify this even further. You can actually, you can simplify it here. You can either time it by 18 or 6. So I'll do that for you guys. Negative 6. 9 times 2 is 18. X squared plus 9k newtons. We'll go even further, and you can break this down since 6 goes into 18. And what we have here is negative 1/3 x squared plus 9 kilonewtons V of x. So there you go. This is your equation that you will have to use to solve for this diagram. At any point, at any given point, meaning at anything in x, so I can plug in 3, 4, 5, and this should give me the exact value of the shear of anywhere on this beam. Once you solve for this, you're golden. Now it's just basically plug in the numbers and putting in there. So please memorize this formula. Since I'm running out of rooms, I have to actually get rid of it. So what I'll have to do, just put it all the way to the top. So now I have V of x equals negative 1/3 x squared plus 9 kilonewtons. Okay? Well, what I need to do now is I need to know exactly at 9, since my distributed load continues all the way to the end at 9 meters, I want to know exactly what is my shear at this point. So, V of 9 equals negative 1/3, 9 squared plus 9 kilonewtons. Long story short, V at 9 will give me negative 18 kilonewtons. Okay? Once I solve for that force, now this is where the circle kicks in. Hey, remember what I explained to you here, you have positive decreasing, so anything of any of that distributed load that looks like as if it's positive and decreasing, this is the parabola, or this is the shape that you will be using right here. Or negative increasing, you will use this one right here. So looking back at here, if you look at this distributed load, I see that it's positive, but also decreasing. Would it be decreasing? Yeah. Take a look at this. Positive, decreasing. Negative, increasing. Now in my case, this will actually be considered as negative, increasing. So as you see, I almost confused myself, so now you got to look back at this. What I see here is actually, it's negative because the distributed load is acting down. However, it keeps increasing. So it will be this shape right here. So from this point to this point here, which we said it was negative 18, so somewhere from this point to that, this is the shape that you will have. So in my case, I will draw it down. There you go. The beauty about this now is the best way to verify your answer is, since we have a negative 18, we know that this is static, so the total forces will actually sum up to 0. In our case, we already have a reaction force, NB, which is 18. Negative 18 on 18 is 0. There you go. So this is your shear diagram. Remember the circle? According to this looks to me as it's negative, but it's increasing. So this is the shape that I will draw. Or what you could do is actually just plug it into your calculator and you'll get this parabola shape. If not, this is the best, quickest, short way if you're running out of time and you needed to draw the diagram right away. So this is your shear. Now what we need to do is actually draw your moment. But I see that I'm running out of room here, so what I need to do, I'm going to make this smaller. So I'll just do this. Okay. So here it's negative 18, this is 0. We said here this is positive 9 kilonewtons. This is V of x. Okay? Now we need to do the moment. To do the moment, what you have to do is, if you're not familiar with that, your moment will be the integral of your shear. So moment of x is integral Vx dx. Okay? So what I need to do here will be the integral of this formula, negative 1/3 x squared plus 9 kilonewtons dx. And then you have to consider, here's my moment. You have to consider here what is, if there's any points that are intercepting the y-axis. In our case, we try to solve it according to our free body diagram. We don't have any moment, so we know for a fact our initial point will start out at 0. Okay? After that, you solve for the integral. Here you will have negative 1, x down, so it's negative 1 over 6, x cubed. Sorry guys. This will become 9 plus 9, 9x. Okay, so this is your formula. So now we know the moment. So what I want to do is I want to find out the actual, my peak. I need to know what this distance is, because I know that any point that intercepts the x-axis is going to be my peak for the moment. It's going to be the maximum moment reacting on this beam. So what I want to do here, I'll call that as x.